This slide defines the foundational rule set for all data on the Internet, the Transmission Control Protocol and Internet Protocol, known simply as TCP/IP. To understand why this rule set is necessary, we have to look at the physical reality of a network. A server rack, a laptop, and a mobile phone rely on distinct sets of hardware components and operating systems. As the text block on this slide outlines, TCP/IP bridges that physical gap through abstraction. It establishes a strict set of communication guidelines that are implemented uniformly, regardless of the underlying hardware. The main purpose of this uniformity is to secure communication over long distances. Because the rules are standardized, a local network in one country can exchange data packets with a server located thousands of miles away. TCP/IP operates as a universal translator. Without it, the Internet would remain a fragmented collection of isolated, incompatible local networks. This diagram illustrates exactly how TCP/IP organizes that translation. It utilizes a modular, four-layer vertical architecture. The stack consists of the application layer at the top, followed by the transport layer, the internet layer, and finally the network layer at the base. These layers operate on a strict top-down execution pipeline called sequential encapsulation. Data from the user starts at the top layer and moves downward, picking up specific networking instructions at each stop. To understand how networks function, we must track a single piece of user data as it physically descends through these four specific layers. By examining the distinct, self-contained function of each layer, the technical complexity of routing global data breaks down into a logical, step-by-step mechanical process. Here, we see the definition of the application layer. It sits at the top of the TCP/IP model and is the point where the user directly interacts with the network. This layer translates user intent, like clicking a link or typing an email, into network-ready raw data by relying on high-level software protocols. As this slide details, everyday web browsing relies on HTTP, or its encrypted variant HTTPS, to transfer text and video. Meanwhile, network managers utilize SNMP to oversee connected devices. Moving down the protocol list, this layer also manages SMTP to execute email transfers, DNS to map human-readable domain names to IP addresses, and SSH to securely encrypt connections. Once the user software generates this protocol-specific raw data, the application layer immediately hands it downward to the next tier for processing. The application layer dictates exactly what data needs to be sent, but it possesses no instructions on how to physically transport it. This brings us to the transport layer, where raw data is structurally prepared for its journey. TCP takes this data block, dividing it into smaller segments, then attaches a specific TCP header to the front of each one. The transport layer uses these headers to determine transmission rate, enforce flow control, and sequence the data for correct reassembly later. Furthermore, it guarantees connection reliability by performing error correction if any segments are lost during transit. While TCP is the standard, this layer also utilizes the User Datagram Protocol, or UDP. UDP drops the error checking to maximize pure transmission speed, which is why it is used for live video and gaming. The transport layer operates as a shipping manager, guaranteeing that segments will arrive sequentially and intact regardless of underlying network congestion. The payload now drops into the internet layer, where TCP segments are converted into datagrams. To reach a destination, the data needs logical addressing, so this layer attaches an IP header, explicitly stamping the source and destination IP addresses. This slide outlines why those addresses are applied. Logical addressing enables routing. The layer uses the destination IP to calculate the best and shortest path to transfer the data across interconnected networks. Here we see the core rule at work. The Internet Protocol, either IPv4 or IPv6, is responsible for packet delivery. It's supported by ARP, mapping IPs to physical hardware, and ICMP, which notifies the host of network problems. The Internet layer acts as the system's GPS, providing the exact logical coordinates required to navigate the maze of global routers. We finally reach the base of the stack, the network layer, the lowest operational level. In this final encapsulation step, the entire IP datagram is sealed inside an outer container known as a frame. As the lower text box describes, this layer maps the logical IP addresses established in the previous step directly to the hard-coded physical addresses of the local hardware. Here, we encounter familiar hardware-level protocols. This list features Ethernet and wireless LAN, which govern the actual physical cables and radio frequencies used for the final transmission. At this precise point, the data is no longer digital files or software code. It is translated into a stream of raw physical signals being pushed out of the device's network card. The network layer finalizes the payload, translating digital intent into real-world physical transit. To understand why the TCP/IP framework is the global standard, we must look at the historical alternative, the older 7-layer OSI model. This comparison chart demonstrates TCP/IP's pragmatic design. It consolidated the top 3 OSI layers, application, presentation, and session, into a single application layer. It similarly streamlined the bottom, compressing the data link and physical layers into a singular network layer. While the OSI model remains useful for strict academic categorization, TCP/IP won the protocol wars because its consolidated architecture prioritizes efficient, real-world data routing. Every downward step through the stack represents the concept of data encapsulation. The raw user payload gains a necessary layer of structured metadata at each tier to ensure it can travel. Once fully encapsulated, that outer frame flies across copper wires, fiber optics, or cellular networks to reach its destination device. Upon arrival, the receiving device processes the data in reverse, called de-encapsulation. It moves from bottom to top, systematically stripping away a network frame, the IP header, and the TCP header, until the raw data is handed directly to the receiving application. The true utility of the TCP/IP stack is its compartmentalization. Because discrete networking tasks are isolated to discrete layers, hardware engineers can replace physical cables, while software developers build new web browsers, allowing the internet to scale without ever breaking the transmission chain.